This is another impulse momentum problem. You can tell that because it has the graph of force versus time, and it also gives you an initial velocity and asks you what the final velocity is. So there's velocities, forces, and time. That's an impulse momentum problem. I also picked this problem out because it has the pulleys and it involves drawing a detailed free body diagram. So the first step to drawing a free body diagram is to draw a closed loop around the object of interest. So there we go, right there. So the next step is to draw everything that's in that closed red loop. So I've got the block, I've got these two pulleys coming out, and the 4 pieces of rope. That's all in the red loop, and there's also this piece of rope on the left. The next step is to draw all the forces that are in the closed loop. And so we have the weight, so that will be mg. There's a normal force. This problem says there's no friction. And now the last step is to draw all the forces that red loop has cut through. And so the first thing to notice is that this here, let me highlight the rope. That's all one rope. And so when ropes go around pulleys like that, the force is the same. And so we've cut through 4 pieces of that rope, and each one will have a tension of the same force, F1. On the left side, we've only cut through 1 rope, so that will be F2. Okay, and this will all equal mass times acceleration, but because we're using momentum, we won't use that. So the impulse momentum equation again is the initial momentum, mv1, plus the sum of all the impulse, which is the integral of force over time. And remember, impulse is a vector equation, so we're going to just do the x component. And that will equal the momentum afterwards. Okay, so we do know that the mass is 30 kilograms, and the initial velocity was 5 meters per second to the left. So I'm going to call to the right positive, so that's negative 30 times 5. Plus, okay, we have the integral to the right of 4 f1s dt minus the integral of 1 f2 dt. And that's going to equal the mass times the new velocity. So this is going to boil down to finding, let me take the 4 out, the integral of f1 dt from 0 to 6 seconds minus the integral of f2 dt from 0 to 6 seconds, and then solving for v2x. Well, the integral of f1 dt is just the area under the f1 curve, and so the graph is in newtons and seconds, so that's correct. So the area under the f1 curve, there's this small triangle of 10, the small rectangle of 10 times 2, and then there's a trapezoid I see of average height of 2 plus 4 and a width of 2. And then there's the rectangle on the end of 30 times 3. Oops. The average height of that trapezoid is 10 plus 30. So what I'm doing is I'm getting this area first, then I'm getting this area next, and then I'm getting this area last. Okay, so area 1 is 10 times 2. The area of that trapezoid is the average of 10 and 30 times the width of 2. And the last one is 30 times 2. That's the width of 2. Okay, so multiplying that all out, I get 120 newtons times second. And so similarly, we're going to do the integral of 0 to 6 of f2 dt. And so the area under that blue curve is 40 times 4 plus 1/2. The average height of the trapezoid is 40 plus 10, half of that times the width of 2. And that equals 210 newtons seconds. Okay, so let's put everything in. We got minus 150 plus 4 times the integral of f1 dt minus the integral of f2 dt will equal 30 times v2x, and that comes out to 120 equals 30 v2x, and v2x therefore is 4 meters per second positive, which means to the right.